Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to focus on circle geometry again, theorem number 3 for mathematics grade 11. And this is the theorem that says perpendicular bisector of chord passes through circle center. On that note, please don't forget to click the subscribe button and hit the notification bell so you don't miss out on more videos we upload in the future. Now back to this video. We have a lot to cover, so let's start. In total, we're going to look at, in summary, the corollary of a theorem. This is a third in a series of three, a trio of theorems, and this one basically combines all three, and we call that a corollary, and you'll see in a moment what that is about. Number two, we're going to look at step one, and that will be understanding the theorem in detail. We're going to do a deep dive on the theorem. Number three, we're going to look at step two of the theorem process, the proving process, and that is the goal. What is the goal and how are we going to do this is step number 3, which is point number 4, the strategy. How are we going to do this? Number 5, we're going to look at how to apply this theorem, looking at questions from past exam papers. Let's start. Before we do anything, let's look at a corollary and how it is related to both the theorem and the converse. Remember, theorem 1 is the one that we started with. That's the main theorem. Theorem 1 is the theorem that says perpendicular line from center bisects chord. So basically, we're told that if a line is drawn from the center of the circle perpendicular to the chord, then it bisects the chord in a circle. That's theorem 1. Now, the converse of the theorem 1 is theorem 2, which says it goes the reverse. It is the reverse of theorem 1. It says if a line is drawn from the center of the circle to the midpoint of the chord, all right, then it is perpendicular to the chord. If it goes to the midpoint, it means that it bisects the chord. So basically, if a line drawn from the center of a circle in such a way that it bisects the chord, then the line is perpendicular to the chord. So that's the reverse of theorem number 1. Don't get confused. Understand who is who in the zoo. Please go watch those two past videos, number 1 and number 2 in this series that I've already posted, so you can understand exactly how a theorem is related to a converse and now combine all of them in a corollary. Now, what is a corollary? A corollary is the theorem that combines both qualities of these theorems, number 1 and number 2. So now this is what we are coming with. The perpendicularity and the bisection is done. So we're combining both theorem 1 and theorem 2. Theorem 1, we're saying that a line drawn perpendicular to the chord AB and also bisects it. In other words, it joins to the midpoint. It goes through the midpoint. That's what we call the perpendicular bisector of chord. And we're saying that this theorem, the corollary, say if that is the case, if you have a perpendicular bisector of the chord, then it has to go through the center of the circle. That's how the corollary is now collaborating everything. Let's start. Let's look at the corollary, which is theorem number 3, which is the theorem that brings both theorem 1 and 2 together. Now the theorem goes, perpendicular bisector of chord passes through circle center. And there is a statement. This is what the diagram looks like. So you start with perpendicular bisector. We're required to prove that it goes through the center. But that's what we're going to come to. First, let's analyze the theorem. Number 1. Let's analyze the theorem. So the theorem goes, if the perpendicular bisector of a chord is drawn. Perpendicular bisector, perpendicular means meets at right angles, 90 degrees. Bisector means cut into two equal parts. So a perpendicular bisector is a line that cuts at 90 degrees angles. It cuts another line at 90 degrees angles into two equal parts. If the perpendicular bisector of a chord is drawn, then the line will pass through the center of the circle. That's what the theorem says. That's how our analysis. Now, this is the reason we use whenever we use this theorem, perpendicular bisector through center. So whenever you have this perpendicular bisector, you know that it will go through the center of the circle. The center of the circle will be somewhere along those lines. What are we given? We are given that circle with midpoint P on chord AB. There is the circle. Line QP is drawn. There is line QP, such that angle QPA is equal to angle QPB is equal to right angles. It is drawn perpendicular, and point P is right in the middle. It's the midpoint. Same story, line RP is also drawn such that same scenario. Angle RPB equals to angle RPA, both equal to 90 degrees. It's also drawn perpendicular. What are we required to prove? That is step number 2. What are we required to prove then? What is the goal? What are we required to prove? We are required to prove that the circle center O lies on the line PR. How are we going to do that is the strategy. What will the strategy be? Notice that we already have right angle triangles formed. So obviously, for ease of proof, using the method of congruency to do this will be very, very strategic, and it will be very helpful and easy. But what is it that we are trying to prove? We are basically going to prove that whatever point we draw or plot on the line RP, it will end up equidistant from A and B, as long as P is the midpoint of the chord. So it does not matter whether we draw Q, AQ will be equal to QB. If we draw R, RA will be equal to RB. That's what we are trying to prove, that these points, the points will be equidistant, meaning that the hypotenuses will be equal. So meaning that, therefore, that means the center of the circle will definitely be somewhere in that line, because that's the ultimate point where every point along on the circle is equidistant. So if we have a scenario where if we draw any line, it is point on this line RP, it is equidistant. Therefore, that one of those points will have to be the center of the circle. That's the whole strategy. So let's start. That's the whole point. That's what I mean. So we're going to use congruency. We will use congruency. And in this congruency, we are going to use, we're trying to prove that the hypotenuses are equal. So the best one to use will not be RHS, it will be side angle side. That's the proof of congruency that will be best. Let's start. In triangle QPA and triangle QPB, let's start with that triangle and then we'll do the other one. In triangle QPA and triangle QPB, OQP is equals to QP. QP is equals to QP, and that is a common side. Next, angle QPA equals to angle QPB, both equal to 90 degrees, that's given. Angle QPA equals to angle QPB, both equal to 90 degrees, and that is given. Then lastly, the sides. PA equals to PB, that is also given. PA equals to PB, that is also given. Therefore, the two triangles are congruent. Therefore, triangle QPA is congruent to triangle QPB. And the reason is side angle side, meaning that therefore, the hypotenuse is QA is equal to QB. Therefore, QA is equals to QB, the hypotenuse. Meaning, therefore, that if QA is equals to QB, that means Q is equidistant. Q is equidistant to both A and B. Therefore, Q is equidistant to A and B. Equidistant to both A and B. To both A and B. To A and B. Now let's do the same and prove that R is equidistant to A and B. Let's go. Let's do that. In triangle RPA, and triangle RPB, RP is common. RP equals to RP. That is the common side. Next, angle RPA equals to angle RPB, both equal to 90 degrees. Angle RPA equals to angle RPB, both equal to 90 degrees, and this is given. And lastly, PA equals to PB, that is also given. PA equals to PB, that was given. Therefore, the two triangles are congruent. The two triangles are congruent, meaning that therefore R is equidistant to A, meaning that RA equals to RB. Therefore, RA equals to RB, meaning that therefore R is equidistant to both A and B. Now, therefore, the conclusion we can make is that it does not matter how far we extend this line RP, as long as it's still in the circle. The points are going to be, the points we go along the way will all be equidistant. All points will be equidistant. We can show that all points drawn along, all points drawn on the line RP, all points drawn on line RP will be equidistant. Will be equidistant to A and B. Equidistant to A and B. Will be equidistant to A and B. Meaning, therefore, the center of the circle lies along RP. Therefore, the center of the circle, the center O of the circle, lies on line RP, because it is the ultimate equidistant, because it is equidistant to all points. Because center O is equidistant to all points. To all points in the circle. And that is how you prove that therefore circle center O lies on the line PR. Now let's look at some examples from a past paper. This one comes from the November 2015 Department of Education, grade 11 CAPS, paper 2. And question 11 goes, in the diagram, the vertices A, B, and C, here the vertices A, B, and C of triangle ABC are concyclic, meaning they lie within the same circle. EB and EC are tangents, they are EB and EC, are tangents to the circle at B and C respectively. BE meets the circle at B, and this one is a tangent at C. T is a point on AB. T is a point on AB such that TE is parallel to AC, such that TE is parallel to AC. TE is parallel to AC. Let's draw that in the same color so it pops up. Okay, let's make it purple. TE is parallel to EC. All right. These two lines are parallel. Okay, you can see they're parallel there. All right. Such that TE is parallel to AC, BC cuts TE in F. BC cuts TE in F. Now question 11.1, prove that angle B1 equals to angle T3. Prove that angle B1 equals to angle T3. Notice that BE is a tangent, so naturally let's use the 10-chord theorem and see if it will help us. All right, B1, okay, so we need to prove that T3 is equals to B1. But according to the 10-chord theorem, here is the strategy. According to the 10-chord theorem, B1 will be equal to A, because the chord, the tangent and the chord, here is the chord, let's make it blue so you can see. Here is the tangent and there is the chord. The line, the angle formed by the tangent and the chord, this angle B1, is equal to the line, is equal to the angle subtended by the same chord BC in the alternate segment. Here is the minor segment and there is the major segment. The line subtended by chord BC is A. I mean the angle. So therefore B1 equals to angle A. The reason is 10-chord theorem. Okay, we are required to prove that B1 equals to T3. 11.1. Required to prove angle B1 equals to angle T3. All right, so far we've got B1, angle B1 equals to angle A. Reason 10-chord theorem. You can just write 10-chord. Or you can write 10-chord theorem to save time, just write tangent chord. Next, there, so B1 is equals to A, but notice that AC is parallel to TC, and they therefore form a shape of F. I'm going to also draw it in purple. So you see, it forms in, whenever you see parallel lines, they always go with these angles, fan X angles. So you need to look out for a shape of an F, a U or C if you prefer, an N or Z if you prefer, and usually also followed by an X or alternate angles, or vertically opposite. So these are your corresponding angles, co-interior angles, and alternate angles, and then vertically opposite angles. So these two will be equal. Therefore, A equals to T3 because AC is parallel to TE, and these are corresponding angles. F forms corresponding angles. But angle T3 equals to angle A, or angle A equals to T3. Reason, those two lines that are parallel. AC is parallel to TE, all corresponding angles. AC parallel to TC, alternate angles. No, it's corresponding angles, sorry. F forms corresponding angles. The alternate angles are formed by AZ or N, corresponding angles. Therefore, because B1 is equals to A and A is also equals to T3, therefore, B1 is equal to T3. Angle T3, let's see. Yes. B1, we've shown that angle B1 equals to angle A, but angle A equals to angle T3. Therefore, angle T3 equals to angle B1, which is what we were trying to prove. Number 11.2, prove that TBEC is a cyclic quadrilateral. TBEC, prove that TBEC is a cyclic quadrilateral. Now here are three ways you can prove a cyclic quadrilateral. Proof of cyclic quad. Here are three ways you can prove a cyclic quadrilateral. The first one is when your opposite angles are supplementary, meaning add up to 180 degrees. All right. Number two, when the exterior angle of a cyclic quad is equal to the interior opposite angle. Number three, when angles in the same segment are equal. When angles in same segment are equal. Angles in same segment equal. Now let's see which one will be best for this scenario. We want to prove that TBEC is a cyclic quadrilateral. Okay, opposite angles supplementary. There is no way we can prove that they will add up to 180 degrees because we're not given values for angles. Same story with the external angle of the cyclic quad. We cannot say for sure because we're not given values for these angles. However, we can try and see if the angles in the same segment are equal without the values. What will those angles in the same segment be? It could be any of these. It could be B1 and T2. It could be T3 and C3. It could be any. You could look at any chord and then find like angles in same segment. So let's use T3 and C3. All right. How are we going to use this? So let's use angles in same segment. B1 and C3 are actually equal because BE and CE are tangents from the same point. So they are equal. BE, so let's use that. But notice that C3 will be equal to, how will it be equal to? Okay, but C3, yes. T3 is already equal to B. Okay, perfect. All right, let's prove that B1 equals to C3. And because B1 is equal to T3, then therefore they will be equal. Let's go. BE is equals to CE. 11.2. BE equals to CE, and the reason is tangents from same point. Tangents from same point. Tangents from same point. Now that BE is equals to CE, therefore the base angles are equal. Therefore CE equals to B1. Therefore B1 equals to C. Let's see what? B1 equals to C3. Base angles, isosceles triangle. B1 equals to C3, and the reason is you can just say BE equals to CE, or BE equals to CE, or you can say base angles isosceles triangle. Base angles isosceles triangle. Okay. Therefore, but B1 is equal to, let's see, but B1 is equal to T3. Proven. But B1 equals to angle T3. We've already proven that. Therefore, angle C3 is equal to angle T3. And these are angles in the same segment. Therefore, TBEC is a cyclic quadrilateral. Therefore, TBEC is a cyclic quad, and the reason is that angles in same segment equal. Angles in same segment equal. There. 11.3. Prove that ET bisects angle BTC. Notice that as I am proving and showing things, I do not erase. I leave them there because they become very useful in the future when we prove other questions. Prove that ET bisects BTC. ET bisects BT. If ET bisects BTC, therefore it means that ultimately we must prove that T3 is equals to angle T2. All right, so we're required to prove that angle T3 equals to angle T2. That's number 11.3. We are required to prove that angle T3 equals to angle T2. Required to prove that T3 equals to T2. Angle T3 equals to angle T2. How do we go about that? Let's go back and see what we already have. How do we prove that T3 is equals to T2? Easy peasy. Easy peasy. Now look at it. Angle B1 and angle T2 are angles in the same segment of quadrilateral TBEC. Angle B1 equals to angle T2. Angle B1 equals to angle T2. Reason is angles in same segment on TBEC. Cyclic quad. But angle B1 equals to angle T3. Proven. But angle B1 equals to angle T3. This has already been proven. Therefore, angle, let's see, angle T2 equals to angle T3. Therefore, angle T2 equals to angle T3. Meaning that, therefore, TE bisects, it bisects angles. It means it must be cut it in equal halves. It bisects angle TBC. is it TBC? BTC, sorry, angle BTC, sorry. Angle BTC, it bisects angle BTC. There, we've proven that. 11.4. If it is given that TB is a tangent to the circle through BF and E. B, F, and E, that is the triangle. Let's draw the circle so you can see what we are working with. Let's change the color of the circle to something else, maybe yellow. All right, there we go. Let's make it smaller, just a little smaller. Make sure it goes through all the corners. There we go. There we go. Okay, there we go. All right, now we are given that BT or TB is a tangent to this circle, and we are supposed to prove, let's see, prove that TB equals to TC. If TB equals to TC, then we need to prove that B2 this angle, we need to prove, ultimately we need to prove B2 is equals to angle C2. So we're required to prove that TB equals to TC. 11.4. We're required to prove TB equals to TC. In other words, ultimately we are required to prove that the angles, the base angles, are equal. That C2 equals to B2. Okay, basically required to prove that B2, angle B2 equals to C2. You have to look at it in every way possible so that it's easy for you to prove that. So let's start. We know that we are given that BT is the tangent to the circle at B of this, the circle through BFE. So therefore angle B2 will be equal to angle E2, tan chord theorem. There is the chord BF and the tangent, so it subtends the angle in the alternate segment. There is the alternate segment, and there is it. So B2, angle B2 equals to angle E2. Angle B2 equals to angle E2. And the reason is tan chord. How then do we connect E2 and C2? Let's go back. From here, how is perfect? This is TBEC is a cyclic quadrilateral, so E2 and C2 are angles in same segment. So E2 equals to C2, but angle E2 equals to angle C2. And these are angles in same segment of cyclic quad TBEC. That's cyclic quadrilateral. So E2, angle E2 equals to angle C2 because of that. Therefore, angle C2 is equals to B2, angle B2. They're both equal to angle C2. I mean, both are equal to angle E2. Therefore, angle B2 is equal to angle C2. Both equal angle E2. Meaning that therefore TB equals to TC. The reason is base angles of isos triangle, base angles equal, isos triangle equal. Okay, there. So let's go back. So TB equals to, because C2, angle C2 equals to angle B2. So we're here. Now the main question that is related to the theorem we just proven in this video, the main point is this last question. Hence prove that T is the center of the circle through A, B, and C. To prove that any point is the center of the circle, you need to prove it is equidistant to all the corners of the shape that is encircled inscribed in that circle. So we need to prove, what are we required to prove? We are required to prove basically that TB equals to TC equals to TA. We've already proven that TB equals to TC. We need to prove that all of that equals to TA. How do we prove TA? So basically we're required to prove that TA equals to TC equals to TB. All right, that is 11.5. We are required to prove T is the center of the circle T is the center of the circle. In other words, TA equals to TB equals to TC. TA equals to TB equals to TC. We've already proven that TB equals to TC. So how do we prove that TA equals to TC? Easy. We'll just prove that this angle C1 is equal to angle A. How do we do that? We already have these two parallel lines. Let's add this line and form AZ. This Z will be able to show us something. Remember, whenever we have parallel lines, we can either form an FU, N, or Z, and an X. Sometimes, not always. So now, notice that TE, TC, and AC form AZ. There is a Z. Therefore, it means that angle T2 is equals to angle C1. C1 equals to angle T2. Angle C1 equals to angle T2. And the reason is parallel lines alternate angles. Angle C1 equals to angle T2. Angle C1 equals to angle T2. The reason is the parallel lines alternate angles. Okay, what are the parallel lines again? Let's go. I think it's AC. AC and TE. AC is parallel to TE. AC parallel to TE. Alternate angles. But we've already proven that. So this angle is equals to, but we've already proven that T2 is equal to A. Proven. But T2, angle T2 equals to angle A. But angle T2 equals to angle A. Already proven. Meaning that therefore, angle C1 is equal to angle A. Meaning that, therefore, because angle C1 equals to angle A, it means that TC equals to TA. Therefore, TC equals to TA. Therefore, TC is equal to TA. Therefore, TC equals to TA. Okay, isosceles triangle. Base angles equal. Base angles of isosceles triangle equal. Base angles isosceles triangle equal. But TC equals to TB already equals to TB, and that is proven. Meaning that TA equals to TB equals to TC. Meaning that therefore, it proves that therefore T is equidistant from A, B, and C. Or from, I'm not sure which one to use, A, B, and C. Meaning that therefore T is the center of the circle. The center is the point where that is equidistant to every point on the circle. And that is how you prove that. And with that, we've come to the end of this video. Thank you so much for watching. I'll see you in the next one. Bye-bye.